Hello everybody and welcome to a new video on this channel. Today I will show you how you can calculate the discrete Fourier transform using matrix notation. Therefore we have to create a so-called discrete Fourier transform matrix that we can apply to our desired signal, and then we will get the discrete Fourier transform of that signal. Also, the other way around is possible. We can apply the conjugate of this matrix to our discrete Fourier transform, and then we will get our original signal. In general, when we want to calculate the discrete Fourier transform using a computer or FPGA or what else, we use the ifft, the Fast Fourier Transform. They are doing the same, but with different complexity. The ifft, the Fast Fourier Transform, is a very efficient way of calculating the discrete Fourier transform. But today I want to show you how you can create the DFT using matrix notation. So let's directly head over to our workspace and create this discrete Fourier transform matrix and demonstrate it with a small example. So first we are clearing our workspace, we are closing all maybe opened windows, and we are clearing our command line. Whenever it comes to DFT or FFT, we have to define the length of the DFT or FFT. Let's say in this case a length of 4-point DFT. And this discrete Fourier transform matrix has some special properties. I will link you the corresponding literature below the video in the description. But we need one important parameter, let's call it W or omega, and this one is exponential of minus y 2 times pi divided by the length of the DFT FFT. And this value here, this expression, is calculating the nth root of unity. In this case, we are calculating the 4th root of unity. Exponential minus y or j imaginary 2 times pi divided by the length of the FFT. So, and with this nth root of unity or 4th root of unity, we have to create a matrix, it's only in helping matrix, which has the dimension n times n. So in our example, 4 rows and 4 columns. And each entry of this matrix is only a copy of W. So therefore we can use the repmat command, which is replicating a certain scalar value or matrix as many times as we want. In our case, we want to replicate our value omega to a matrix with 4 rows and 4 columns. So n DFT rows, n DFT columns. Let's fire it up to see what happened. So we now have a helping matrix WW with 4 rows and 4 columns, and each entry has the same value, the 4th root of unity. And now we need a third variable, which is defining the powers that we will apply to each element in our matrix WW. Therefore we create a vector, let's call it n. It starts from 0 and goes to n DFT minus 1. So in our case, 0, 1, 2, 3. But that's not the end of the story. We have to create again a matrix which has the following expression: n transposed times n. If you transpose a vector and multiply it with its non-transposed version, you will get a matrix. And if we fire it up, it will result in this thing here. So this matrix nn is defining the exponent that we apply to each element of our matrix WW. Meaning the first row of WW will be will have an exponent of 0, the first row of nn. The second row of our matrix WW will have the exponent defined by the second row of nn, so 0, 1, 2, 3. The third row of WW will have exponents defined by the third row of nn, so 0, 2, 4, 6. The fourth row of WW will have exponents defined by the fourth row of NN, 0, 3, 6, 9. For sure, if we want to calculate a longer FFT or DFT, this matrix will have a larger dimension, but the scheme behind still stays the same. So, and what we now will do is create the discrete Fourier transform matrix. Let's call it W with capital letters, and it's nothing more than our helping matrix WW, so this body here, and we want to apply an exponent defined by our matrix NN to each element of WW. Therefore, here means that we WW to the power of NN, and with this point we indicate, okay, apply the exponent defined in NN to each element, to each corresponding element in WW. And the result will be this one here. And this is our discrete Fourier transform matrix. In the literature you will see that there are also some normalization factors, that each element will be normalized, for example, to the square root of the length of the DFT, or only to the or will be normalized to the length of the DFT. But in this example we will not use any normalization factor in order to produce the same result as Octave will give us if we would use the FFT command. So this is our DFT matrix. DFT matrix. So now we want to test the matrix by applying it to a signal. Let's create an arbitrary signal X with 4 elements in it, for example 5, 6, 1, 2. This is our vector from which we want to calculate our DFT, FFT. And first let's use the FFT command in order to calculate the FFT of X. I will output it as column vector because this one here is a row vector, and after multiplying it with W we will get the column vector. So for comparison I force the FFT output to be a column vector by writing point and asterisk here. And so let's fire it up. So this is the FFT of our signal X. And now let's see if we will get the same result if we apply our signal W to our signal X. Therefore we only type W times X, and in this case X transposed, because we have an n times n matrix and we have to multiply it with a column vector, and X is a row vector, so we have to force X to be a column vector. Let's fire it up, and as we can see we get exactly the same output as we would have used the FFT. And we can also go the other way around. Let's store the output here in X capital letters. And now we want to generate our X original. Let's call it X hat. And therefore we just take the conjugate of our matrix omega and multiply it with X. And in this case we need a normalization factor. This is because Octave and MATLAB have some special normalization factors in the FFTs, which is in this case the length of the FFT. So let's fire it up. And here it is. We have our original signal back again, 5612, which was our original signal. So we have now a way of using a matrix notation in order to generate our DFT, discrete Fourier transform, or the other way around. We want to calculate our original signal by applying the conjugate of this discrete Fourier transform matrix to our calculated DFT, and we produce the same output as we would use the FFT. Again, here we can also verify it by calculating the ifft of the FFT, and then also our original signal should be there. And here it is, 5612, and our solution using the matrix notation 5612. So yeah, that's it for today. Very short video, but I thought it could be interesting of seeing how to calculate the DFT using matrix notation. If you like this video, please subscribe, give me a thumbs up, and we will see us the next time. Bye bye.